thanks. Now, I can tell you about a lot of great videos throughout this entire 3-day practice, but that one
is blowing it up, isn't it?
Yes. Everybody loves it because practical solutions, right? Like we can talk about machines and concepts and theory, but these were practical solutions. And oh, by the way, anybody with mild steel headers on a race car, their head just exploded.
Their heart attack.
Their head just exploded. Like, what? John, welcome. Thank you.
Hey, good afternoon.
So let's get started right away. We've got so much positive feedback from everybody out there. Put your questions in the chat section, but so many practical advances and just ways to save time and do things the right way that you've amassed over your years and years of experience.
Well, I actually, watching that, I forgot about some of that stuff we did, but I wish I would have seen that video 50 years ago. It would have saved me a lot of grief. But the good thing about it is it's all cheap. Anything that's on there you can do, and if you're going to work on engines, you can afford that. Some of the things we talked about. But it's hopefully it'll help some people. I think everybody it ought to ring their bell in one or two places, and maybe and you might be able to tell people, because I don't know. You can go back and watch these videos again.
Yes, absolutely. They're all there. They're going to be posted. Not only that, once this is all finished, they're going to be blasting these out in all kinds of different forms. I guarantee that video that we just watched, there's going to be parts and pieces of it, and the whole thing available in many different places.
Well, the good thing, we saw lots of questions were about what the part numbers were, and you listed out those on the slides, so you'll be able to go back and rewind it and watch it when the recording's available to get all those part numbers. Because I know when I was filming you, John, with that, and you pulled out the Scotch-Brite grinding disc for the wheel, and I was like, why didn't I think of that? What a brilliant idea. And I'm like, oh, dummy. Yeah, one of the comments, I'm not sure if you saw it, was from our good buddy Ben Strader, that, John, you have a really polite way of making us all feel dumb.
Well,
Thanks, John.
But I'm pretty humbled today, because I've watched a good bit of your presentations and stuff, and I'm kind of feeling a little bit like Elmer Fudd or something compared to those guys, because they've got all this really high-tech stuff, and here I am showing you how to shorten a bolt. But at the same time, that's practical stuff that you can use, and a couple things that I was thinking about was, you can still do a reasonably good job and be successful at this business without, the absolute best equipment,
Exactly.
And, some of our stuff is getting a little bit older, but we chose to put our money into a 5-axis CNC machine for machining heads for more castings. So, we're still using older stuff, but boy, every one of those things I saw on your presentation so far, I'd sure like to have.
Well, exactly. And some of the comments, we're going to need all you viewers out there to get over it, though, and come up with some real questions, because it's like, thank you so much. This is amazing. Strader's out there, all hail King Kaase. And one of our guys, he goes, this is the first segment that didn't make me want to spend all my money, but helped me save a little bit of money. So thank you on behalf of Ken.
Yeah, exactly.
Yeah, I understand. I've been in business for quite a while, and we're not as frugal as you might think, but we try and be sensible and not, we don't want to have any time that you would be making more payments than you could afford. So we have to, buy one thing at a time, and that's just kind of the way the businesses are, And but boy, there sure is some nice equipment out there today.
Oh yeah. Well, when you mentioned you have your 5-axis to do your cylinder heads, you think back at the beginning of your career, could you have ever imagined having your own line of cylinder heads and what that would have encompassed and taken to do?
It's funny the way things progress. When we started on the Boss 429 heads, we were just reproducing and making better the original equipment. And I really sort of wanted to do it because I wanted to run that engine in the Engine Masters. And the stuff that was out there wasn't quite good enough. So we had no idea that we'd be as successful at selling them as we were. And it's a good thing, because, to bite off one of those big projects is pretty expensive when you start looking at the patterns and stuff. And maybe at the time it wasn't a real practical choice because we didn't know if we could sell them. But you know, at this time we're pretty much ground zero for Boss 429s in the world. You know, we do a lot of, we do heads and manifolds and valve covers and make a lot of those parts ourselves, and there are patterns. But you know, we also do a wedge head, and there's some stuff out there that's pretty good. Some of it, you know, we did, and it's hard to make them better. But we've got a couple heads for wedge 429s that are really overachievers. They really do well. And I wouldn't really say I had a vision of building those heads 20 years ago. I was like, oh, someday I'm going to build this head. It's just something that kind of happened, and we did it, you know.
Excellent, excellent. All right, we've got some questions for you right off the bat. Greg wants to know, for the lathe-made cam bearing driver mandrels, any special materials required, or just turned down 6061 aluminum?
We never did make any out of aluminum, and you could try it. It would probably be okay, but it might be, the one that I made was made out of bronze, like the same stuff you'd make valve seats out of, but it just happened to be what was on the end of the lathe that day, you know? The other one was a piece of steel, and it's the same thing. It was just whatever was close by. So, you know, probably aluminum would be fine. You'd know pretty quick, because it would stick to it if it didn't like it. But I think as long as you lubricate it up good, but the really important part of that is it has to have a nice radius on the entry and the exit of where it hits that bigger spot. And, you know, just like everything else in the shop, we do that, and make it on a lathe or something, and you hold it between your fingers and take it over that Scotch-Brite wheel and run it around. And, you know, so the Scotch-Brite wheel did most of the radiuses on the edges.
Excellent. And people have questions about the Scotch-Brite wheel too, like part numbers. Everybody wants partners. That is good stuff. Next question, though, regarding any plans to offer a spread exhaust bolt pattern on the P51 or SR71 heads?
Probably not. I think you'd have to change the casting, and you know, anytime we've made any real big improvements to the exhaust other than what's there now, it really didn't help any. Like, we put bigger valves in, it didn't help, and we ported the exhaust port where we went into the head bolt hole a pretty good bit, and we just back to back it. It really didn't show up much, you know. It'd be nice if it had a big round port there and all, and then you built your own headers. But most of those SR71 heads, most of them go in a passenger car of some kind, and some of them do use factory headers. I don't know that we'd probably make them with a wider bolt pattern.
Excellent. Here's another one. This one from another Joe out there. Thanks, John, for everything. You talk about aluminum rod bolts and caps seating in after initial run-in. At what point do you recommend retorquing, and do you untorque and then retorque?
So those are good questions. You know, years ago, it's funny how this business works, but if you have a problem, even if it was 30 years ago, it always stays with you. And it used to be on aluminum rod engines. This is back when I worked for Dyno Don and stuff. Is if you took an aluminum rod engine and you checked the bearings in it, it'd always blow up on the next run. You know, so you got to where you really didn't like to disturb them once they were torqued. You know, but today the stuff is so much better. You know, the aluminum, the bolts, the way it's the engineering, everything is so much better. Those certainly aren't the rules anymore. But we actually got to the point where we, like, over a 6-month off season on these engines, that these rods are torqued to 135 and stuff, we tell the guys to pull the pan off and loosen them up. You know, because I just don't like to have them torqued that much when they're just sitting for that long. There's a lot of stress in that rod. Think about it's trying to blow the outside of the rod off, you know, with all that torque on it. or split the you know, through the bolt hole out to the outside or something. There's no telling how much tension's in it. So, you know, we'd rather back them off and torque them to 50 foot-pounds or something, and then when they get ready to torque them back. But I don't really like to disturb stuff once it's torqued. And usually the parts are good enough today that they're not really going to probably move too much. And that 135, you know, the 135 foot-pounds, if the serration sank in 1,000ths or something, it's going to be way on the safe side still. And the way they've got the washers and stuff on the couple different types of rods that we use, so we don't really have hardly any problem with a washer sinking in anymore. So generally, when we take an engine apart, one of those big engines, it'll have 30 runs on it, and they're hard runs too. And you know, we'll take a good look at them, and most of the time they're torqued just like they were, and I mean, you can't budge them, so they don't really sink in. They usually do pretty good.
Excellent, excellent. Keep those questions coming, folks. Mark wants to know, what are the most important factors for being able to run less valve spring in a 9,000 RPM engine?
I think that's mostly has something to do with Billy Godbolt, I guess. You know, it's everything's important in that valve train, but I think certainly the most important is usually the lobe itself. So. And you would like to use always the least spring that you need. Like, we don't have this much experience with it anymore, but they tell me on a 500-inch cars, those guys would, you know, a Pro Stock car, they would never, ever, ever put all new valve springs on an engine during a race. You know, it's not going to happen because it hurts the power. You know, because they're fresh and they're maybe a little bit more pressure, but there's more friction because of the way they're rubbing together and everything. And they like to change one or two, but not, I think, more than that, because they hurt the power when you put new springs on them. And
Break in the spring.
I know that, you know, a couple of years ago on my Edsel on the Engine Masters, I was getting into a little bit of valve float, and I put stronger springs on it. It hurt at 15 horse, and there's no question it hurt at 15 horse. And then I took the exhaust off, and I put the weak ones back on the exhaust because I figured the intake was the problem. And when I put the weak ones back on the exhaust, it picked up 7. So, you know, the more spring you have on it versus what you need, the less. I mean, it'll hurt the power. No, you know, it'll absolutely hurt the power. But to have a light spring, you've got to have everything really working in your favor. So it's got to have good lobes, and you know, the whole valve train's one big spring. I mean, a bunch of different springs. I mean, you know, the rocker's a spring, the push rod's a spring, the valve's a spring, and the valve spring's a spring, the retainer's a spring, and all those things are working against each other. And you got one that's a little bit weaker than you want, and then they get into a sync where, you know, I guess the frequencies all of a sudden they match, or something happens wrong. Billy can tell us, but you know, you would like to have a really good valve train to run a light spring, but then, you know, if you've got a push rod that weighs 1 pound, maybe that light spring isn't going to like that push rod. So there's a lot comes into it.
Excellent. All right, here's one. John, we saw Warren yesterday. WJ was in yesterday, John. We saw Warren said he wasn't very fond of the Hemi, especially for NA. What made you attracted to them for your Fords? And that one coming from Ben Strait.
Well, see, our Hemis, what we call the Hemi, the Boss, you know, the big inch Pro Stock engines, they're big motors, and they only run, you know, 8,500 RPM, and they do everything about right for the chamber. Really works good on those. The Chevys are a copy of the Ford, and they're all really the same head. So we've tried to build those same cylinder heads on a 500-inch motor, and they're just not very good at all. So the shorter stroke and the high RPM, it doesn't appear to work very well, at least for us. And you know, and Warren's right. You know, the what they've got and the evolution of all that cylinder head to where they're at today is what works the best for that boring, that stroke, and that RPM. You know, and when we try to do that with the Ford or the Hemi, it's not very good up high. But if they take that same head like the GM Pro Stock head and make a big inch motor out of it, they're not quite as good. So there's something about ours that likes the RPM range we run in. And, you know, sometimes you just have to do what works and forget about why, you know?
Yeah, listen to the engine, right? Let it speak to you.
Yeah, we like to know why, but sometimes you really never do. It's too costly to find out why.
Got it. Jason is out there, wants to know, John, can you talk a little bit more about rod bolt stretch procedure a little more, specifically verifying stretch after a certain torque value?
Well, I think I said in that video, and I gave it away. We don't do the stretch as much as we should probably, but I think that honestly, I really believe that they're more important on a steel rod engine, and the steel rod deal would be because the friction where the threads are and stuff, it might vary a little bit from one tap to another or whatever. You know, you got steel on steel, and it doesn't glide as easy. Think how easy that bolt glides in the aluminum. You know, the aluminum's like it's just slick, and there's never any ratcheting or squeaking or anything. You know, when you're torquing a bolt in aluminum. So we don't. In aluminum rods, we kind of go by the torque, and we know that that's what they were torqued to when they were honed and everything else, and that's probably good enough. But you know, if it's a steel rod engine that's kind of highly stressed, you really ought to take the time to check the stretch on them before. You know, well, I mean, it has to be before and after you torque them, but you'd want to be in that number that they're giving you. Whether it's funny because some of the really good bolts, like the car bolts and stuff that used to be for Carillas, I don't think they were 5.5 to 6 thousandths maybe, but then there's other stuff that's 7 or 7.5, and depends on what the bolt's made out of and how long it is. But you know, I would say that you really ought to look at it.
Well, that's a great thing.
Especially a steel rod motor, you really ought to keep up with it and check it. But sometimes with us, we know, you know, on crate motors and stuff, we know they're torqued to 75 or 85 foot-pounds or whichever rod we're using, and they almost never don't come out right. So on those, you know, you can torque them and not really worry about it. But, you know, if it's a really good quality rod and a good quality bolt that's, you know, they're a couple $1,000 set of rods, you know, and $400 set of bolts, I would probably check the stretch on them.
Well, that's the great thing. You said ARP, they have the recommended lubes, they have recommended stretch values, they have the tools. ARP has everything you need to get that job done right, so that you have that little bit of extra insurance, and you can put one of those demons to rest in your head, just, you know, over your shoulder, telling you, did you do that right? Did you do that right? Yeah, you don't worry about that one.
And on that note, let me just mention that there are several questions about assembly lube, like aluminum rods and steel bolts. What is used? Which thread lubricant are you using when torquing rod bolts? So several people have questions in that area.
Okay.
Well, you know, on all the aluminum rods that we would use, the company usually tells you, but they don't get too carried away with something special. Usually it's about a 50 weight oil or some kind of 40 weight, or it's not really an assembly lube necessarily. You know, when you get to the steel rods, there's different kinds. I mean, the Carillas come with a little tube of stuff that comes with them usually, but they're kind of an anti-seize looking moly stuff. Some of them have a little coppery look to them even. And you know, years ago, the biggest problem we used to have was when years ago we used to run titanium rods, and it was a titanium thread there, and man, you had to use this GM stuff we call peanut butter on them. But they'd screech, you know, they'd almost throw blue sparks out when you torqued them. They were awful. So, you know, it depends on the material. But you really need to kind of stick with what the rod company tells you they want you to use. But I think ultimately, if you were, you know, a steel rod though, if you were checking the stretch and you got the stretch that it's supposed to have, it wouldn't matter what you used on it, you know?
Well, that's the thing. If you got the stretch right, then you're right. You're spot on. And that's when I know the guys at ARP spent a lot of time developing their ultra torque lube. And the whole point was so that when you had a given amount of torque for their steel
Yeah.
parts, it would give you a consistent amount of stretch. Because they really
That's
recognize
right.
that some people aren't going to always measure stretch. So the idea is, hey, if we have a lube that's going to give you consistent torque value to stretch value, keep that equation pretty linear, then it gives you some safety factor there. But of course, I got to do my part for Chris Radsky, who's one of our sponsors of this event. Make sure if you have ARP bolts, follow their recommendations. They have all the tech that you need to make sure you get it done right.
Well, and it's consistent. I mean, it always works right, but you can always tell if you've been torquing rods because your hands are going to be black for the next day or two, right?
There you go. Bob has
It gets in your pores.
Yeah.
We've got time for a couple more. Bob Wells wants to know, windage trays, yes or no, louver or screen, and minimum clearance to counter weights and rods?
I'm listening.
Windage trays are huge, you know, or the pan done right. But, you know, that on a lot of these wet sumps especially, that's the single most important of the engine. I mean, if it's not right, if you have an uncovered sump, and if the crank can see, if it's got a line of sight where if the crankshaft can see where the pickup is in the bottom, it's probably going to blow up as the motor gets bigger. So, like if it's a 600-inch motor, it's got more of a chance of blowing up than it's a 514-inch motor because there's more wind and stuff. And anything you can do to shield it. I mean, a lot of the stuff we do will have a pan that it'll have a little window where the pickup goes through it to go into the bottom, and we'll actually have to do something to the pickup and have a cover on it or something so that the wind can't see that little window where you had to, you know, run the little pickup box into the bottom of the wet sump pan. But you know, windage tray will do the same thing, so that's good. But there's, you know, I've learned some real lessons on that. Either it'll blow up, or it'll hurt the power if you don't have it right. And you know, there was one time on one of the Engine Masters, I screwed up and had this Chevy that I built, and it had a big open pan in it. I thought it was fine because it was about a foot deep, you know. And when I got all done, I think I finished second by not very much. I didn't lose by much. And then when I got home, I got all mad, and Rosso sent me one of their catalog pans I put on, and it was about 30 horse better, you know. So, and that absolutely would have won. So, you know, those things you do not forget. Okay.
There you go. All right, we're just about out of time, John. But I'm going to throw one last question in for Charles because he's asking, and I want to know. The question is basically, where did you get your knowledge from? Did you go to school for engine machining, or did you learn it all from Dyno Don, or somewhere else, or both? Let's all end off with that one. Where did this all?
Well, you know what? I learned a lot more about life, I think, from Dyno Don, than because he wasn't really a machinist so much, you know. But I've been around a lot of different people that we did work for, and every one of them will teach you something. You just really have to just kind of listen. But, you know, I'm starting my 54th year of working on engines. So, you know, you learn stuff from your employees. You'll learn stuff from your customers. You'll learn stuff from other racers. And sometimes you learn stuff from yourself at 3 in the morning when you wake up and you have an epiphany that what you were doing wrong, you know, or something. So, and you know, certainly you learn a whole lot from all your mistakes and blow-ups and things you did wrong, because you generally try not to repeat those things you did wrong. So mostly it's just by doing and trying to figure out. If you do it every day, you know, you're going to get a pretty good, I don't know what you want to call it, a pretty good group of knowledge in your head that of what's important and what's not, what not to screw up on, and maybe the big thing is what's important. What do you need to worry about, and what do you need to say? Well, this isn't a big deal.
Excellent, John. Excellent work. 9-time Engine Master for a reason. We really appreciate you taking the time. The video is incredible. The live Q&A even better. Thank you for spending time with us here at the Engine Performance Expo.
Oh, no problem. I will say one last thing. I noticed I think I had one of the sheets upside down for the part numbers, so I hope people can look at that and stop the video. Can you stop the video?
They've all done screen captures left and right. They're all posting about it. It's all over Twitter. It's everywhere, so we're good.
All right.
Excellent. John, thank you so much. Lake, this has been incredible.
Oh, yes. Knew it was going to be fantastic.
So what we're going to do is we're going to keep on trucking. And yes, someone is asking, like, when are you going to give away the short block? Well, right near the end. You got to stay with us. But next up, Jimmy Barton, another video. We're getting ready as we're coming down the stretch here at the Engine Performance Expo.
Hi, Lake. I'm Jimmy Barton from Robert Yates Racing Engines. We're going to share some insight on the LS GM motor as a racing engine versus a production engine. This engine was originally designed as an emission control engine, so it has some inherent manufactured in properties from GM where they heat the exhaust port up on it to make the catalytic converters and the exhaust work for the emissions control, and that doesn't feasibly work with the race engines. What they do is they heat the exhaust port up by blocking the head gasket off where it doesn't get water around the spark plug.
Ooh.
And in a race engine and an extended, prolonged, wide open throttle situation, you get too much heat and it tends to cause head gasket damage and cylinder head damage. There was several good people here designed a water system and worked on some head gaskets and stuff on the dyno for a long time to get where we're at today to keep from burning the engines up. Well, this is a modified head gasket. This is a stock, well, it's a Cometics, but it is a replica of a stock head gasket. And the only thing different in it is the block already has the water holes in it, as you can see here. Well, on the GM production engine, that's blocked off on the head gasket. And basically all we did was open those holes up, which if you were to put it on the motor, you would see that the spark plug was in the center of the cylinder on each side. So by opening these holes up down here, all we did was put water around the spark plug and up over the chamber, which is not there in the emissions motor. The factory head gasket does not have the holes, and the reason it doesn't is to make the emissions part of the engine work properly.
So it's restricting the flow.
It's restricting the flow of the water and the head at the exhaust, but still cooling the chamber. Well, because of our wide open throttle situation and the heat over a duration of time, you could possibly build a steam pocket. So you need to release that and have water flow through it somewhat to cool the engine properly at the wide open throttle situations. Well, for that, GM has a tube here that is an air bleed in their cylinder heads, and they use the front ones on like the Corvettes and stuff. They don't necessarily use all four of them. Sometimes they do. Well, they have pieces on the factory motor that bolt on here on the front that goes back to the radiator to vent air out of this engine, because this is the highest point. The filler point is actually below the top of the block, so you have to vent the air at the highest point. So we just put aftermarket vents on it, which is the same as GM, and then we put a little water tank on it up here on top of the valley cover. This big line feeds back to the suction side of the water pump. So it's constantly pulling the water that these are putting into the tank back to the inlet side of the water pump. And this here, being the highest point on the motor, this line here goes back to the radiator. This line here goes back to a surge tank, which is open to atmospheric air. So it lets it pump the air into the surge tank, which is filled with water, so it can't suck. If it draws back in when it cools off, it fills the water. Because even if you get the air out of it and you lose water, it's going to build more steam. So you have to keep it full of water in order to not build steam. Now, the lines are made just so that one crosses here, and it's just a packaging issue is the way to get them on there. And they go to those fittings on the cylinder head. And this is where the air plus water comes out. The water separates, the air comes to the top, it leaves the system through a water-filled can so that when the motor cools off, as it heats up, it expands.
Right.
pushes the air out and the water out, and as it cools down, it contracts. So you got to have water so that it will draw water back in and not air, because if it draws air back in, you're inducing air to the situation, and you've got the same problem you had.
Exactly.
And then we did, through hours of research on the dyno, we did all 4 corners to take more air, because this being a left turn motor, it tends to want to get air in the left side. So you have to bleed all 4 corners to get it to do that. As was brought to my attention, we need to talk about the way that this works. And the reason there's a T in the center and the back, and the front lines are very closely similar to the same length, is because if you put just a fitting over here that comes up and goes back to the tank, and then run a line over here, if they're not equal lengths, you have less resistance at this corner, and it'll flow more water and air out of here than it does over here. So you want to have equal length hoses so that it draws the same amount. So I mean, that's why the front hoses are very similar in length, and the rear section is very similar in length. Well, the results of doing the water system is you have less detonation. You know, the chamber temperature is down because of not creating a steam pocket and making the engine more efficient as the water system goes. The timing, you can add maybe 1 more degree of timing to it than you could before, just because you've got a cooler combustion chamber temperature. More forgiving. And that's the key to this engine, is to keep it relatively inexpensive and make it safe for the racer so they can tune it and it stays together. Because if it don't stay together, it costs the same amount of money as any other high dollar race engine. So we have to make it to where it runs all year.
Back here in our studio at Engine Performance Expo, taking a street engine and making it a high-performance engine, there's definitely going to be some considerations that have to be taken. And I'm very excited to have Lake Speed Jr. at a ring grinder. He's Mr. Total Seal. My goodness, we get to see you in your genuine element.
Exactly, sir. So it was cool to see Jimmy Barton talk about those little nuances between a street motor and what happens when you take it and make it a race motor. And obviously cooling is a consideration. They talked about at length, and having the right tools to do the job. Okay, here's another tool to do the job. So ring end gaps. And this is a question that I know Keith and Kevin and Bobby and everybody gets the tech line of Total Seal all the time.
Every day.
What should my ring end gaps be? So we're going to go down that road a little bit, and let's talk about conceptually about ring end gaps for a little bit, and then we'll actually go through a little demo. We're going to show you, we're actually going to set the end gaps on this gas ported piston ring. So it's a little fancy high-tech piece.
Yes.
Yeah, you know, so we'll go through that. We got all of our tools here. Got our feeler gauge. We know it's not a ring, it's a ring compressor. We don't have the block back here, so we're going to do a little Hollywood magic, and we're just going to use the ring compressor as our gauge, so we can go take some end gap off and put it back in and measure it and go through that. But the whole reason is, why do we have ring end gap?
Why do we have ring end gap, Lake?
So the one reason is you have to have ring end gap to be able to install it on the piston. That would be kind of a neat thing you need to be able to do.
Yes.
Now, once you get it installed on the piston, the idea is that ring end gap needs to be able to compensate for the growth in the ring with temperature. We had Pat Musey on earlier, and what was he saying? If you could take the cylinder heads off right at the end of the run,
Glowing red.
right. So what happens to metal when it gets hot?
It expands.
Exactly.
Even I know this stuff, folks.
So the more cylinder pressure you run, the more power you're making, the more heat that's going into the ring. Therefore, you need a larger end gap. So, of course, we don't have to do all the mental gymnastics. Our buddy Randy Neal gave us that term the other day. At Total Seal, we actually have a complete listing of recommended end gaps based on the application. For example, like Pat's application, you're running nitrous. Big power, big heat, bigger end gap. So that top top ring needs a bigger end gap because it's going to see the bulk of the heat. So the idea of that is you need that bigger gap so that it doesn't butt. Because what happens is if your rings butt, bad things happen. Because now it's trying to expand, it can cause increased cylinder wear, it can do lots of damage to your engine, so you don't want that. So, and nitrous is an interesting topic of conversation in regards to end gap because, you know, a normally aspirated engine is only going to be able to develop so much heat with just an air-fuel mixture. But when you add nitrous, now you've got this accelerant that's going to drive that temperature up. But you're not always running the nitrous with full hit going in the bottle. So what happens is you have to set that end gap for your worst case scenario, the most amount of nitrous you're running, which means that every moment you're running that engine without that, you have a bigger end gap. And you're like, well, why does that matter? Well, back to Mr. Hydrocarbon guy, this is called blow-by. Blow-by, it allows the combustion gases that would normally be driving the piston to make power to escape past the piston. That's a lack of efficiency. So ideally, you want your end gaps when the engine's running to be almost zero, is where you want to be. That's kind of hard to figure, which is why Joe Moriarty years ago invented the total seal piston ring, which back then was the only thing we had was a gapless ring. And the idea of the gapless ring is it overlaps. It was two overlapping rings that closed that gap. It would allow you to have that big end gap for that max cylinder pressure, max temperature, but then at normal driving conditions, at lower temperatures, you still didn't have that increased blow-by. So it could compensate. Now, that's the idea of a gapless ring is, as you have talked to Keith on the show, Hidden Horsepower, you know, there's applications for that. Now, this particular ring I'm holding is basically a NASCAR type ring that's a gas-ported ring. And
which it's teeny tiny.
It's small.
There's not a lot going on there.
But it's a seal. I mean, you got to think about it. We were talking about the piston the other day with Jimmy Barton, and he said, no, the wrist pin is the backbone of the piston. It's the structural component. Piston rings are not a structural component of the piston. It's a seal. You wouldn't think about putting an iron gasket between your head and your block because it can't move around. This needs to be able to flex, right? Gaskets are soft. They're designed to conform. Rings are designed to conform, which is one reason why Total Seal invented the Total Conform ring, where it's got these little radial notches in the back that allow the ring to conform. Back to the gas-ported ring, it can conform to the distortion of the piston because that piston isn't completely strong out there on the edges. Like Jimmy said, you moved the wrist pin in, but now the outside edges can move. So the gas ports in the ring are doing a couple of things. Not only allowing the gas pressure to get behind the ring to increase ring seal, it's also allowing the ring to move and seal against the bottom of the groove, which is also a big area of ring sealing. But back to the beginning topic, ring end gap. We know we want to have the correct gap for that top ring and the second ring. And there's some theory about second ring end gap. And let's address that real quick. Some guys say the old school way of doing it was you set the same end gap for the top ring and the bottom ring, knowing the top ring is going to be hotter, so it's going to grow more. So there's a second gap that will actually in operation be wider. That would allow that any gases trapped between the top ring and the second ring to escape. Now, what's happening in the modern low tension rings when you're getting to a, say, 3 millimeter or a 2 millimeter style oil ring, what we're seeing is they actually like having a little bit wider second end gap when you have lower ring tension to use that blow-by to help evacuate the oil from the oil ring, because that oil ring, when it gets small, has less tension than, say, a 3/16 ring. So there's some people that have done that. We won't get into all the details right now. Maybe another time, another video, we get some maybe a guy like Brad Peters. If you're watching, Brad, I want you on here. We can talk about this, buddy.
Yeah, this isn't the last one of these.
No. So anyway, so let's talk about how you set the gap. So once you've got the idea of what gap you want, the power ring filer is going to get the job done for you. And hey, my boss, Matt Hartford, the guys at Total Seal, they've made this super easy. Even somebody like me can do it. So what you do is you put the ring on the ring filer. So what we're going to do here is we're going to hold the ring in position with this. That's going to be the clamp. But you want to set the right radius because you don't want to cut it crooked. What you're going to do is we're going to put the ring down here like this. we're going to move the ring and set it against the square it against the grinding wheel. Now this little device out here is going to be able to adjust out and give us the radius. Now we're only doing one ring. The nice thing about this is once the radius is set, you can run through 8 rings, boom, boom, or 4 rings, or however many, back to back to back. So we're going to set this right here. So now it's clamped down. We know it's locked in. This is locked in. We're all good. So now what we're going to do is we're going to set our dial indicator to 0. So now we know we're beginning at 0. In this case, we pre-measured it. There was 22 thousandths in gap. We want to take it out. Say we want to take it out to, say, 30 thousandths in gap, all right? So what we're going to do is now we're going to turn on the ring filer. We set it to 0. Now we're just going to begin to move and grind it in. Now there's a couple ways you can do this. Now I'll back up here just for a second. Some guys like using this as the chop method, right? And you can do that with a bigger ring. But because this is a tiny itty bitty ring, you don't want to bend that ring because it's pretty thin. So what we're going to do is we're just going to start it down here and we're going to roll it back this way. And I'm just holding that table down, dialing it in. And I was at 22, so I'm going to take 8 thousandths off the dial indicator. And when I put it back in the ring compressor, simulating our bore, that should give us right at 30 thousandths. And I'm just going real slow, letting it creep up on it, because again, this is a thin ring, and you don't want to hurt your ring. You don't want to bend it. It needs to be square and level and flat. So there we go, right at 8 thousandths. Turn that off, bring it up. Now the deburring wheel over here, we can use that to deburr it, because we're just moving along for time here. I'm going to skip that step. But now we've opened that gap up. We're going to set it here in our ring compressor. Again, I know I don't have a squaring tool. I know how wrong I'm doing this, so just know that.
We're on TV.
Yeah. So I made some marks to set it in here. Closest I'm going to get it. It was 22. Oh, it's a whole lot more than that now. So let's get out our 30 thousandths feeler gauge. Roll her over to it. Now I can drop it right in. Boom. Done. It's that simple. So with the right tools to do the job, you can rip through this, and it's way better than that hand grinder.
Oh my goodness, and I still see those every now and again in use, guys cranking them out.
Oh, yeah.
But if you have an opportunity like this, and it's a great machine, and this is available at Total Seal, obviously we got to deburr that before we leave the set today.
Oh, we're not.
Yeah.
We would never, ever put what we just did in an engine. Just know that.
Yeah.
But this is for demonstration purposes only.
Well, I think it is great, and it's just another example. We've learned a lot over the course of the week about different tools that have made jobs more efficient and easier, and here's one. If you're spending a lot of time doing this, you can get them all the same. You get uniformity, you have efficiency, and isn't that what it's all about? You save some time.
Exactly. And the whole idea is we want to have, efficiency throughout the whole engine and efficiency in the time it takes to build the engine. So having the time, a tool that saves you time, now you're not just worried about your top end gap and your second end gap. You can actually deal on your oil ring end gap, because that's part of, for a vacuum engine, a dry sump engine that's pulling vacuum, or even a wet sump motor that's got a vacuum pump. You can actually gain some power and get better blow by dialing around your end gaps on the oil rails on the oil ring. So a little, hidden horsepower there, but you got to look into it. So this makes that job easier, because if anyone's ever tried to grind an oil ring that's hard steel, you don't want to do it with that grinder. This thing makes the job a lot easier.
Oh, excellent work, and I appreciate it. And obviously, this is something you can find more information about at the Total Seal website. They sell them, as you can imagine. And of course, the end gap, the recommended end cap, is available on the web as well, right?
Yes, all the recommendations are right there on the website.
What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not